topics that we're going to try to discuss here include what I have written above. Some of the terms that we're going to discuss are primes. I'm going to start by actually going over what a divisor means. Then we're going to talk about GCDs, or greatest common divisors. We're going to talk about elements being zero divisors, mod n, and we're going to talk about elements or integers being invertible, mod n. Some of the results we'll see along the way are these results I have written in between here. An interesting fact, sometimes called Bezout's identity or Bezout's lemma. And then we'll also have an occasion to see Euclid's theorem about prime numbers. So there's a couple other results we'll probably see along the way, but those are some highlighted ones I wanted to point out. Okay, so let's start by just recalling the definition of divides. Let's just say recall that we say A divides B means you can write B as a number C times A, where everything here, A and B and this new number C, are all integers. We could also, so we could say A divides B. We mentioned that in a previous discussion. We also mentioned saying that B is a multiple of A. And now I just want to make sure I have this word on the record, which is A is a divisor of B. So it's easy to get, at least for me, it's a little easy to get tripped up when we start thinking about divisors for not just integers, but specifically for positive integers. So I'll maybe switch colors here and just say for positive integers. So now if A and B are integers that are bigger than 0, right, to say A is a divisor of B, well, that will tell me, this will imply, yes, of course it means A times another integer is B, but it will also tell me that A has to be smaller than or equal to B. And again, I assumed everything's positive, so A is between 0 and B. Okay, so I just want you to keep that in mind, that for a lot of what we're going to discuss, specifically for the next topic that comes up, a lot of what we're going to discuss, when I'm dealing with positive numbers and I throw around the word divisor, I'm going to be thinking of a divisor as a smaller number than the second number, the number playing the role of B. So, for example, we could ask for the divisors of the integer, let's say 8. And you might write them down. You might say, well, 1 divides into 8, 2 divides into 8, 4 divides into 8, and 8 divides into 8. Those are all its divisors, but actually all I wrote there were its positive divisors. I also have -1, of course. I also have -2, -4, and -8. If I contrast that with the divisors of -8, okay, well, I'm actually going to have the exact same list of integers, right? All the things that divided 8 also divide -8, of course. And I just want to point out that on my second example over here on the right, it is no longer true that the divisors are less than -8. In fact, if you look at this example, all of these divisors here are bigger than -8. So, in a lot of what I'm going to say, sometimes I'm going to use the fact that divisors are smaller than the number they're dividing into, than their quotient. But I'm really only allowed to do that when I'm thinking about positive things, right? So going back to the left here, the positive divisors of 8 are these numbers. And that's usually when people are speaking about divisors of a positive number, we usually only mean these. But technically, we could refer to both. So I'll try to be specific, but just keep in mind I might slip and forget to say, oh, I'm talking about the positive divisors in this instance. Okay, so super duper important definition is a definition of what we call a prime number. And I'm going to define it for positive integers. So a natural number, p, that's in boldface N for natural, sorry about that. A natural number p is a prime number, and I'm going to actually offer you two definitions here. Another way to say it is, I'll just call it is a prime, or is prime. And here's the definition. If and only if, here's the common definition. The only positive divisors of p are the number 1 and p itself. This is probably the definition of prime that you're used to. This captures the way you've thought about this word in the past, right? According to this part of the definition, right, we have examples of prime numbers 2 and 3 and 5 and 7, not 9, but 11 and 13, and on and on and on. Okay, there's one little hiccup with this definition. If I leave my definition stated technically exactly like this, then I am forced to say that the number 1 is prime. And I don't know, but if you're aware of this, or if you've heard this or not, but mathematicians are really bothered by the number 1 being declared a prime number. It's not that the number 1 isn't special, it's that what we're really trying to capture about prime numbers doesn't really apply to the number 1. We're going to want to think of the prime numbers as sort of our basic building blocks for all other numbers. And the number 1 does not play a role in building up other numbers this way. Right? So to make mathematicians happy, to get rid of the number 1, I then have to adjust my definition. I have to say a natural number p is called prime if the only positive divisors are 1 and p, and if p is bigger than 1. Right? This just gets rid of 1 being called prime. You should actually, if you have time, look around on YouTube for different videos of why isn't 1 a prime number. There are lots of interesting reasons for this choice. If you want to summarize a lot of those reasons in a sort of cheeky way, you might say mathematicians define prime numbers to not include the number 1 because it's more convenient for them. Okay, so let me give you an alternate definition of prime numbers that maybe feels a little more natural. And it was a former research undergrad student of mine who reminded me of this definition. So here's an alternate definition that actually sounds more elegant. P in the naturals is prime if and only if, so here's our definition, P has exactly 2 positive divisors. Okay, so this requires a little more thought to see that it's actually the same, it's capturing the same numbers in this definition as the one I have boxed above. But let's think about this. Let's maybe switch to another color here. let's think about this. What are the divisors of 2? Well, the divisors of 2, so I'll write my number over here. I'll write my number over here, and then, oh gosh, I can't make a straight line. And then I'll make the number of positive divisors in this column. So if I pick as my number 2, there's only 2 divisors, 1 and 2. If I pick so this deserves to be called prime by my definition. If I pick the number 3, there's still only 2 divisors, the numbers 1 and 3. Only 2 positive divisors. So this is prime. But if I look at the number 4, well, now I'm a bit troubled because I have 3 divisors. The number 1, the number 2, and the number 4 itself. So this is not prime. Right, and you can pick other numbers that you know aren't prime, like, oh, I don't know, 12. How many divisors does that have? Well, let me write them over here. It has 1, 2, 3, 4, 6, 8, and 12. Dear God, that has a lot of divisors. There's just an abundant amount of divisors here. There's 1, 2, 3, 4, 5, 6, 7. This has, is it 7? 1, 2, 3, 4, 5, 6, 7. Am I 3 times 4? Oh, I wrote down 8. 8's not a, sorry, 8 is not a divisor of 12. I can't do arithmetic. Okay, there we go. 1, 2, 3, 4, 5, 6. So it's got 6 divisors. It is really not prime. And if you go by this definition and now you say, hey, is the number 1 prime? Well, it's interesting, how many positive divisors does the number 1 have? It only has 1 positive divisor, just itself. And so it's not prime, albeit for a different reason. It's got fewer than 2 positive divisors. Okay, so these are both great definitions for prime. Whichever one you like to think about, it doesn't make much of a difference. But the sort of first thing I should tell you about prime numbers is a really important theorem, and it's called the fundamental theorem of arithmetic. Okay, so what is this fundamental theorem of arithmetic? It's fundamental to arithmetic, and yet, if you're anything like me, I hadn't heard this until I got to college. I hadn't heard about this result. And I'm going to say what this says, but I'm first going to say it in words. And here's what it says. The primes are sort of the periodic table for all of numbers. Right? Just like all the elements in the periodic table are what all of matter tends to be made out of. The prime numbers are the few numbers that all other numbers are made out of. So the primes are the building blocks, if you will, for the entirety of the natural numbers. Every natural number is built out of primes. So let me say this in a more mathy way. So in other words, if, let's say, n is a natural number, then, and I'll switch to a more interesting color, n is equal to some product of prime numbers. I don't know exactly how many. I'll just stop it like r. So n is nothing but a product, a bunch of prime numbers all multiplied against each other. Okay, I want to be a little careful. I might have some of the prime numbers in this product repeating. So there could be like 2 of these primes, so I might have it squared. There might be 3 of these primes, I might have that number of primes cubed. Right? So more generally, I'm going to have some number, so a1 power, some number of prime 1s, some number of my second prime, right? And all of these ai's are bigger than or equal to 0. So this is saying every number, no matter which one you pick, no matter how ungodly big and unspeakable, no matter how small and silly, you can always write it as a product of primes, right? And so just as an example, you might pick, I don't know, the number, well, let's pick one of the numbers I picked above, 12. And you could say, well, 12 is 3 times 4, and 4 is 2 times 2. And let me write these primes going up. So I have 2 2's times 1 3. I have broken down the number 12 into a bunch of primes all times each other. Right? The number, I don't know, I'll stick with this color. The number, let's maybe try another one, 28. Oh, that's not that interesting of one. Maybe 24. Right? This will be 2 cubed times 3 to the 1. So it has 3 2's and 1 3. All right. So the fundamental theorem of arithmetic is saying something that maybe you kind of feel familiar with, but I will point out the proof of this theorem, the proof or explanation of this, is often delayed. It's not seen. I'll say it's most commonly found in an abstract algebra course. So I am not going to prove this result. Although if you're really interested, you should look up. You could Google or look on YouTube proof of the fundamental theorem of arithmetic. One of the most common places you'll see it is if you're a math major, or you just go on to take a few more math courses, including abstract algebra, and there you'll prove a theorem called the fundamental theorem of finitely generated abelian groups. And it turns out the proof of this tells you the fundamental theorem of arithmetic. It just tells you in this language of these things called groups, specifically abelian groups. Okay, but for us, for our purposes, we're going to take the fundamental theorem of arithmetic as something we're allowed to think about and use. This we're going to take as a fact about numbers and prime numbers. Okay, another interesting fact about prime numbers is the following. I'll just call it a theorem. And it was originally proved by Euclid, I believe, couple thousand years ago. And here's what it says. There are infinitely many prime numbers. So if I go look in all the natural numbers and try to keep track of the primes, I'll never stop looking. They go on forever. This might be something that you're familiar with, this basic idea, but I do want to point out that this is kind of surprising. Why on earth is this kind of surprising? And it's because primes, generally speaking, become rarer and rarer as we search through the naturals. So let me show you what I mean by this. This is the point of what I'm talking about here is what I wrote in green. So what I'm writing in orange here, you could dismiss as a kind of digression, but it's a useful one. It's a historically important or interesting one. So here's what I mean by the primes becoming rarer and rarer. Let's just write a bunch of natural numbers. 1, 2, 3, 4, 5, 6, 7. Maybe I'll keep going. 8, 9, 10, 11, 12, 13, 14, and then 15, 16, 17, 18, 19, 20, 21, and we'll just do one more row of them. 22, 23, 24, 25, 26, 27, And I'll stop at 28, although clearly this keeps going. So here's what happens. Let's say you're going to go looking for primes. And what you notice is you say, okay, well, 1's not a prime. We ruled that out. But I'll sort of circle the ones in red that are prime. So 2 is a prime number. And here's the problem. As soon as you find a prime number, it kills a bunch of other numbers from possibly being prime. Right? What makes 2 prime? It only has 2 divisors, 1 and itself. But so since 2 is prime, every multiple of 2 is now not prime. So anything that 2 divides into cannot be prime. So once 2 is prime, 4 isn't prime, 6 isn't prime, 8 isn't prime, 10 isn't prime, 12 isn't prime, 14 isn't prime, 16's gone, 18's gone, 20's gone, 22's gone, 24, 26, and 28, and all the even numbers are now off the table. None of the even numbers are prime, except this first one, 2. Similarly, 3. You'll say, hey, I can check that 3 is prime, but once you know 3 is prime, suddenly you now know all multiples of 3 are, all future multiples of 3 are not prime. So 6 isn't prime again, 9 isn't prime, 12 we already knew, but it's not prime again, 15 isn't prime, 18 isn't prime also, we knew that one, 21's not prime, 24 is doubly not prime. What's going on here? 24 is not prime, and 27 is not prime. Okay, so now you can keep this up, right? You can say, okay, well, 5 is prime, but that's going to kill a bunch of other prime numbers. 10's gone again, and a bunch of other multiples of 5. 15's gone again, 20's gone again. Oh, we got a new one. 25's now gone. And now look. I wrote down the first 28 natural numbers. Oh, I never crossed out 1. 1, of course, isn't prime, just for silly reasons. Once we found the first 3 primes, 2, 3, and 5, by consequence of those being primes, everything else is off the table, and all the numbers left over here, I'll just circle them in, oh, I don't know, in some other color, in purple. It turns out these numbers that didn't get crossed out, these happen to also be prime. Right? But the more primes you discover, the less likely it is you're going to find future primes, is what this is showing. This process is what you might call a sieve. I always spell sieve wrong. Like, it sort of sorts out the primes, right? And in some sense, they become rarer and rarer. So from that point of view, this result due to Euclid, or originally due to Euclid, written in green above, it's actually surprising. It says, even though every time you find a new prime number, you've just killed infinitely many other numbers from possibly being prime, right? I found 3 was prime, now all future multiples are off the table. Even though that happens, there are still infinitely many primes to always find. And what I'd like to do is show you how Euclid's proof works. So I'll go back to green. So the proof, and it's going to be a proof by contradiction. It's just a lovely proof that if you're going to take a math course that talks about this, that you have to see, right? So here's what we're going to do. We're going to say, well, suppose the set of prime numbers is finite. That's right. We're going to negate the claim. The claim says that there are infinitely many primes, so let's go for a contradiction. Let's suppose that claim's false. Suppose there are finitely many primes. So the set of prime numbers is finite, so I'll call this S, which means, I don't know, there's one first prime, and then there's the next prime, and it stops. I don't know where. Maybe there's 10 million, but there's only finitely many. Okay, all you have to do here is consider a new number. This is what Euclid was so clever in considering. Consider the new number, I'll call it x, where you take all of your finitely many primes and you multiply them. So I'm going to do P1 times P2 and times a P3. Keep multiplying them all in there until you get to Pn. And if you think carefully, if I stopped there with x, this new number I'm calling x right here would not be a prime number, right? Because lots of numbers divide this. Specifically, P1 divides it, because this thing is a multiple of P1. P2 divides this, and P3 is a divisor, right? This has lots of divisors, and here was Euclid's thought, well, let's just add 1 to it. And the point here is that this thing I'm calling x has to be a number. It's a bunch of numbers multiplied plus 1. So x is, this is a, very sort of trivial observation. X is a natural number here. And by the fundamental theorem of arithmetic, x is a product of prime numbers. Right, the fundamental theorem of arithmetic says every natural number, including this weird number x, has to be writable, has to be expressible as a bunch of primes times each other. Right, so x is a product of prime numbers. In particular, this, I'm going to say it this way, there exists a prime number, I'll call it P, that divides x. There has to be a prime number P that divides x. And now we're finally going to get to a contradiction. However, we can check that P1 is not a divisor of x. And let me write off to the side here in maybe red why. Well, let's look at what it means for P1, that first prime in my list, to try to divide x. Again, x is a product of P1 and P2 and P3 all the way up to our last prime number, and then I add 1. Now here's a fact that I'm going to use quite a bit, I believe, in this discussion, in this video, and you might use in some of your homework assignments. Let's see what it would mean for P1 to try to divide this. Well, we already know that P1 divides this piece, because it is clearly a multiple. It's P1 times something. So if P1 were to divide the entire thing, and if P1 were to divide that one piece of it that I squiggly underlined, that would tell us that P1 would then have to divide this number. But wait a minute. If P1 is a divisor of 1, and P1 is positive because it's prime, right? Prime numbers are natural numbers. So P1 divides 1, and it's positive. That means it's got to be a positive divisor of 1. That means it has to be smaller than or equal to 1. The only way P1 could divide 1 is if P1 equaled 1. But then that would mean P1 wasn't a prime number to begin with. And so what this tells us is there's no way P1, that first prime, can divide our number x. If it divided all of x, well, we know it already divides the first chunk of x, then it would have to divide 1, and so this prime would have to be 1. So if P1 divides x, then P1 isn't even a prime, it's the number 1. What does that tell us? There's no way P1 can divide x. There's nothing unique here about the first prime. I could do this for P2, I could do this for P3, I could do it for any of the PIs. So what we really have here, right, is that, I'm just erasing this stuff, that not only does P1 not divide x, but P2 can't divide x, P3 can't, none of the P sub i's can divide x. And so now let's look at where we are in this little green proof. We have, there is a prime number that divides x, but none of the pi's divide x, this implies there is a prime number p that isn't in our set of primes. And that's a contradiction. We said our set of primes was all of them. So, that was sort of Euclid's explanation for why there have to be infinitely many primes. If there's only finitely many primes, multiply them all together, add 1, and this new number has to imply the existence of primes you forgot to put in your set of all primes. I should make one little note here. You can look in different textbooks and notes from other people who teach this sort of material, and it's a common mistake to think that what was going on in this proof was that the product of P1 and P2 up to Pn all plus 1 is prime. I was careful to avoid saying that. What I really said in my proof above wasn't that this is prime, but that this new number can't be divisible by any of the primes we started with. Right, so you can actually check this as a mistake by writing down. You don't have to assume there are finitely many primes to check this. You can write down the first n consecutives, not consecutive, but the first n prime numbers, and start forming this new number where you multiply all those first n primes and add 1. So for example, you could start, okay, let's start with 2 and 3, and then I'm going to add 1. Well, that's 7. That is prime. And then you can say, okay, what about if I do 2 times 3 times 5 and I add 1? Let's see, 2 times 3 is 6, 6 times 5 is 30, 30 plus 1, that's 31. That's also prime. Right, well, it turns out if you do 2 times 3 times 5 times 7 times 11 times 13 plus 1, if you actually do this one, this is not prime. Okay, that was a long digression, if you want to view that as a digression. The point of this little discussion was this, Euclid's theorem, that I'm not trying to put a star next to. There are infinitely many prime numbers. That's surprising when you consider how rare they are, and the proof of it is a lovely proof by induction. Okay, so let's keep going with our discussion. I want to define another couple of words here, so I'll just write definition to let you know that I'm trying to define some stuff. The greatest common divisor of two integers, a and let's say integer b, is the largest positive integer that divides both the integer a and the integer b. So that's what the greatest common divisor of two integers is. And let me show you how to notate it. The notation for this thing, it's actually a pretty obvious notation. It's the GCD of a and b. And if you don't like writing things down in, say, English or natural language words, you can say this is the maximum of all the elements in this set, the maximum of all the integers d, such that d is positive and d divides a and d divides b. Okay, so let's try some examples, right? And then what we're really after is the following. We're going to figure out a way to try and compute a GCD. All right. So let's try some examples, maybe in red. So here's an example. What is the GCD of, I don't know, 6 and 27. And here's one way we could do this. We could quite literally write down all the positive divisors of 6, and we could write down all the positive divisors of 27, and just see which ones they have in common, and then circle the largest one. So for the divisors, the positive divisors of 6, it's 1, 2, 3, and 6. For 27, its divisors are 1, 3, and 9. So I compare this list of positive divisors and I say, okay, what's the biggest? Oh, it's a 3. So the GCD of 6 and 27 is 3. Okay, let's try another example. We could try the GCD of, I'm going to keep my numbers kind of low, maybe of 120, that's a little big, but and 24. And so again, I could write down all the divisors of 120, make a big list of all those positive divisors, write down all the positive divisors of 24, and then circle the biggest one. There's a slightly shorter and similar way to get this number, which is, let me scroll up, to use or think about using this fundamental theorem of arithmetic. Rather than writing down all the divisors of 120 and 24, let me just write down their prime divisors. So it might take you some while to do this, right? I'm not saying everybody knows what the prime divisors of 120 are, but I think there's a 2, and it's going to occur a lot. So that's, let's see, there's a 3, and there's a 5, and I got to think of the 2 that occurs. How many times does that 2 happen? The 2 happens once, 2, 3, I think 4 times. 2 to the 4th. Let's make sure I broke that down into its prime divisors, right? I think that's right, though. Oh, because I'm terrible with arithmetic, let me just double check. So 2 to the 4th times 3 times 5. Oops, I got that. I'm sorry, I have too many 2's. See, it's a good thing I checked. That's not 2 to the 4th, that's 2 cubed. Okay, let's break down 24 into its prime divisors, and that's going to be a 2 cubed times a 3. Okay, so here's what we can do. We can say, okay, rather than circling the divisors they have in common, let's circle the primes they have in common. So there's a 2 and a 3. And how many 2's does 24 have? It's got 3 of them. Oh, and 120 has 3 also. So I get to say it has all 3 2's in common. So this has got to be the greatest common divisor. It's the most amount of primes, right, that they share in their decomposition. So let's see, what is that? That's going to be 24. So the greatest common divisor of these two numbers is 24. All right, let's do another example. Maybe this one will be in kind of a light green, yellowish green. Let's try the GCD of, oh, I don't know, 22 and 65. So this one, you know, maybe we want to write this down, write down all the divisors of both. Maybe we just want to write down the prime divisors of both. You know, for 22, if I write down all of its divisors, it's not that bad. It's 1, it's 2, it's 11, and it's 22. if I wanted to write down all the divisors of 65, I could say, well, it's 1, it's 5, it's 13, and it's 65. Right, had you done this the prime way, you would have said, well, 22 is 2 times 11, broke it up into primes, and 65 is 5 times 13. Okay, but if I go to this list of its positive divisors, what's the biggest positive divisor it has in common? 1. So the GCD of 22 and 65 is just the number 1. Okay, so actually this green example reminds me that we need one more definition. It's almost like this was planned. 2 integers, I'll call them A and B, are said to be relatively prime if, so here's the definition. By the way, some people will call this coprime if, and only if, right, this is a definition, their greatest common divisor is the positive number 1. The only sort of divisor that they share that's positive is the number 1. In other words, they really don't have much in common. And this happened with our above example, right? 22 and 65 are relatively prime. Or, you could call them coprime. And I want to make an important note about this example. Note, neither 22 nor 65 are individually prime. Right? 22 wasn't just divisible by 1 in itself, it was also divisible by 2 and 11. 65 was also divisible by 5 and 13. 22 and 65 are not individually prime. But when you consider them together, compared to one another, they are what we call relatively prime. All right. So, here is a great fact that you guys are in a great position to understand. It's called Bezout's. Some people call it Bezout's identity, and some people call it Bezout's lemma. So I'll just refer to it kinda as both. Bezout was a French mathematician, proved a lot of cool stuff about algebra and number theory. This is one of the more interesting ones, and here's what Bezout's lemma says. The greatest common divisor of 2 integers can always be expressed as a linear combination of the 2 integers a and b. Said more mathematically, whatever the greatest common divisor of these 2 integers is, there is always an integer x, I'll call it, and always an integer y, I'll call it, so that a times x plus b times y is that greatest common divisor. So this is for some integers x and y. This turns out, I know this is kind of a weird thing, it's throwing together a word I mentioned in a previous discussion, linear combination, with a concept we just talked about, greatest common divisor. And it's maybe not so clear. It wasn't clear to me when I first had to think about this theorem, was told to think about it. It's not clear to me why this is useful, but I will just tell you, trust me, this turns out to be a very useful result. Okay, let's try a couple examples of this result. Maybe with, let me pick some of our smaller examples from above. Oh, let's try 6 and 27. So we computed that the greatest common divisor of 6 and 27 is 3. And so Bezout's lemma tells us that there has to be an x and there has to be an integer y so that this is true. So Bezout's lemma says this equation has integer solutions. Now, the way I stated the theorem, it doesn't tell you how to find it, but let's see if we can find what maybe x and y might have to be, or could be, right, to make this true, right? And I think it doesn't take much. You can check. Maybe we'll check this in orange for Bezout. We can check that if I were to use x equals the integer, -4, and y equals the integer 1, this will work. The greatest common divisor 3 is indeed a linear combination of the two integers I was comparing divisors of. Alright, if you want to watch me stumble in a computer recorded video that's eating up all my hard drive space, we can check that relatively prime example of, 22 and 65. The greatest common divisor of these two numbers, these were relatively prime, so their greatest common divisor is 1. So Bezout tells us that there has to be an integer x, and there has to be some other integer y that makes this equation true. And what you can watch me waste a lot of hard drive space on is, what's gonna make this one work, right? And let's see, again, I'll write in orange what I think will work. I think you can check that if x equals -3 and y, x equals +3 and y equals -1, right? We'll have 22 times 3 plus 65 times -1, and I believe that's 66 minus 65, and oh my gosh, I got 1. Okay, so we could keep doing this and see how long it takes me to crank out solutions, but the point is, Bezout's lemma says this always happens. Alright, how on earth does this always happen? It's a little surprising, maybe, right? If I look at the statement of Bezout's theorem written here in orange, this main equation right in the middle here, the left-hand side is a statement about multiplying and dividing, about a biggest common divisor. And the right-hand side is about a linear combination, and those kind of feel like maybe related, but not super related. This is a little mysterious. So why is Bezout's lemma true? Why is Bezout's identity / lemma a true thing? And the answer is kind of lovely. The answer really comes from the division algorithm, which, when you use it in this following way, it's really something that you might call the Euclidean algorithm. This is, again, Euclid sort of using this statement of dividing. Okay, so the Euclidean, when I talk about the Euclidean algorithm or the Euclidean / division algorithm, what I'm really talking about is using the division algorithm to compute the greatest common divisor of two integers. So it turns out Bezout's theorem you can get from figuring out how to compute to the greatest common divisor of two integers. Now if you scroll back up like this, and look at these first three examples of computing a GCD, the first two ways I did it, written here in red and orange, involved writing out all the divisors of my two numbers. Or in the second orange case, writing out all the prime divisors. So that's one way to try and find the GCD of two integers, right? One way, I'll say one, maybe I'll write it, one wildly inefficient way to find the GCD of two integers is to write out all positive divisors and just go looking for the two biggest that are in common. And you can imagine trying to program a computer to tell it to do this. If you start with a big integer a and a big integer b, this is going to be some inefficient searching algorithm. You're going to write down a big list of divisors and a big list of divisors for b, and then you're going to tell it to compare, see which ones it has in common. That's going to take up a lot of time. Even if you say, well, let's just look through the prime divisors. Well, something I didn't emphasize when I mentioned the fundamental theorem of arithmetic is that while it's true every number can be written as a product of primes, finding those prime numbers can be very, very tricky. Not only tricky, it's currently very mysterious how that might work for very large numbers. So this process of computing GCDs that we have right now is really inefficient. It was Euclid who came around and found a better way. Okay, so how does Euclid's way work? So we'll just say, go back to green, Euclid's way / algorithm. We already saw him talk about infinite many primes, so he was interested in how things divide or don't. And this is for finding a GCD. So here's what he does. He says, okay, well, let's go ahead and assume that the integer a is smaller than the integer b. And this isn't a difficult thing to assume, right? Like, if b happens to be smaller than a, then just rename them. This is not a big deal. And then step one, what we're going to do is we're going to try and divide b by a. So we're going to apply the division algorithm, the division statement, one time. Okay, so what do we know from this division algorithm statement? We know that this remainder term, it's not negative, and it's certainly less than a. Well, because the remainder term is less than a, there's nothing stopping us from doing what's going to be the next step. We're going to take a and try and divide it by r. So we're going to apply the division algorithm again. Okay, so I just wanted to comment that when we get to that step, that's why it's okay to do, because r is a smaller number than a, so maybe we'll try and divide it. Okay, but let me motivate why you would do that. We are looking for what I'll call D, the greatest common divisor of a and b. We're looking for this number. And so here's what we know about this number. The number D is positive, and it divides b, and it divides a. Well, because D divides b, it divides this number. That means D divides this entire expression. But because D also divides a, that's part of the definition, D divides this circled expression. Now think about this. D divides the entire box thing. It divides the circled thing. And so that tells me whatever the greatest common divisor is, it has to divide this remainder. Right, so I got D divides B, the whole thing. That means D divides A, so it divides multiples of A. So if D divides the whole box thing, then it divides AQ, and it divides AQ. Then it divides B take away AQ, so D divides R. And so if we apply the division algorithm once, we're going to say, hey, this common divisor divides both A and R. Let's apply the division algorithm to A and R so that D might survive. So what I mean is, since I'm going to apply the division algorithm again, right, I'm going to call at this first stage, this is my first quotient Q1, this is my first remainder R1. Now we're going to apply it again. We're going to divide A by this remainder R, and so we're going to get R1 from above times a new quotient plus a new remainder. And now I'm going to make the same comment, right? What did I learn from this number D? It divided to A and B. That means it divided A and R, R1. Well, now I say, well, D is going to divide A, which means it divides all of this. D divides R1, which means it divides this. So now D also divides R2. So D divides A and R2. D divides R1 and R2. Let's divide R1 and R2. So that's what I'm going to do in my next step, right? I'm going to say, let's divide out R1 divided by R2. So now I'm going to need a third quotient. And now I get a third remainder. And here's where you start seeing the actual algorithm rearing its head, right? How did my thing start? I divided A by B. I take A and divide it by this first remainder, right? Now I take this R1 and divide it by the second remainder. Now I take this second remainder and divide it by this third remainder. So I'm going to get that the second remainder is this third remainder times a fourth quotient plus a fourth remainder. And here's the idea. You're going to repeat this process. And here's where, all of my comp sci students are nervous. We could phrase this as an actually coded, sort of a conditional program, right, to tell a computer to do. But one thing we always want to make sure our programs do is that they stop. And it turns out we can repeat this process until it actually will stop. Until we find a remainder, I'll just call it R sub n, that's 0. So this process will continue for a long time, but eventually we'll get to Rn equals 0. And once we hit this step, then we will have the GCD. So let me show you in an example of how this works. And I'm going to pick a sort of non-trivial example. Let's compute the greatest common divisor of, I believe what I want to do, I'll double check. Let's see, is it? Give me a second. Sorry, I had my example ready to go and now I can't find it. Yeah, okay. Of these two numbers, 287 and 91. Okay, so again, we could write out all the divisors of these two and then circle them, but let's do this the Euclid way, using the division algorithm as an actual algorithm. So I'm going to take the bigger number, call that B, and divide it by the smaller one, 91. So now I need a Q and a remainder. right? Okay, so this is, this is where the work is, right? And it doesn't take that long to see that this is 3 and this is 14. And now my division algorithm said, okay, now go to this number and your remainder and divide those two. So we're going to do 91 is how many multiples of 14? And then we're going to get some new remainder here, right? And it turns out 91 is 6 multiples of 14, and we get a remainder of 7. Okay, and then we go in this stage and we say, okay, 14 and 7, what I'm going to try and do now is take 14 and divide it by 7. That's going to be some number of multiples of 7 plus some remainder. This one is probably pretty easy to do. That's 2, and that's 0. Right, so this is where the algorithm stops because we got a remainder of 0. And now what does it tell us the greatest common divisor is? It's this number, 7. So the GCD of 287 and 91 is 7. Okay, so this always happens. This always happens. You always get the greatest common divisor this way. It's kind of cool, and what I want to comment maybe in orange to make it color match up is how does this help us with Bezout's identity / lemma? And since I have this example here, what I'm going to point out is this algorithm run backwards tells you how to express the GCD as a linear combination of 91 and 287. So here's how it works, right? How exactly am I going to get this? Right here on this line, right, I can say, okay, 7 appeared as a remainder, right? The GCD, according to this process, appeared as a remainder. So 7 is now equal to 91, right, plus a negative 6 times 14. Right, I just rearranged that equation. Okay, but now look what I can do. In my equation from above, this one tells me 14 is equal to 287 plus negative 3 times 91. And now look what I can do. I can plug this 14 in to here. And when I do that, I see that 7 equals 91 plus negative 6 times 287 plus a negative 3 times 91. Sorry for writing off to the side. And so if I sort of distribute all that mess, I'll get 91 plus a negative 6 times 287. Negative 6 and a negative 3 is a plus 18 times 91. And if I combine all my 91s, look what this resulted. I have 19 times 91 plus negative 6 times 287. By running this Euclidean division algorithm backwards, I get Bezout's result, that the greatest common divisor has to be a linear combination of A and B. And so that's how Bezout's theorem works, or sorry, Bezout's lemma. Okay, so just for a couple more minutes, I know this video is going long, I just want to mention 2 more words. One of them is a term that you don't find in textbooks at this stage, so it's kind of different, and it's something called a zero divisor. And I'm specifically going to talk about a zero divisor mod n. So what do I mean by a zero divisor mod n? an integer a is a zero divisor mod n, that's what I'm defining. This means this is true if and only if two things happen. One, a is not already divisible by n. That is, a is not equivalent to 0 mod n. And two, here's the really important part, there exists another integer. It's not 0 mod n, but when you multiply it against a, it turns into 0 modulo n. That's what makes it a quote-unquote zero divisor. A really great example of this happening would be a equals 2, and we could talk about this being a zero divisor mod 6. How do I see that a is a zero divisor mod 6? Well, you need to find another element b so that when you multiply it against a, you get 0 mod 6. But you're not allowed to pick a multiple of 6. b can't already be 0 mod 6. It turns out a sort of opposite, doesn't quite feel like an opposite, notion is this notion of being invertible. Mod n. That's what I'm going to say. This one is mentioned in textbooks for this course, but what I'll say is an integer, again, I'll call it a, is invertible mod n, that's sort of my phrasing, if, and only if, there exists another integer such that a times that other integer is congruent to 1 mod n. Sometimes some textbooks will give this other integer that I've called d, sometimes they'll call it an a with a line on top. That's actually not very good notation. The textbook that we were using, I think uses that. Some people will call it a with a star. Some people will call it a with a little -1, like 1 over a. I'll show you an example of this. So one example would be, oh, let's work an interesting mod. Let's work oh, I don't know. Let me think for a second. 3 is invertible mod 10. Okay, to show that this is a true example, I would need to find another integer so that when I multiply it by 3, the new integer I get is equivalent to 1 mod 10. And you might be scrambling around, but if you check 3 times 7 is of course 21, and if you think about it, that is equivalent to 1 mod 10. Right? Ignoring multiples of 10, 21 is pretty much the same as 1. It's just 2 multiples of 10 separated from 1. Right, I'm going to stop this video in about just a couple minutes, so I'll have to make another one finishing all this stuff up. But what I want to point out is this turns out to be helpful when solving what you might call linear congruence equations. So I'll just make sort of a quick analogy. By this, I mean thinking about invertible things and thinking about what I've called zero divisors. So why is this helpful? Well, let's just consider the following examples. Maybe the first one will be in this kind of blue shade. This one won't be a congruence equation. This is just going to be 3 times x equals 15. And when you guys were first learning some algebra, maybe in, I don't know, when you nerds first started it, like probably in kindergarten or something, but whatever grade it was you guys started doing this, what you would probably do is like divide by 3 on both sides, right? And so when you said divide by 3, that's one way to say it. You would get x now equals 15 divided by 3, so x would equal 5. But I just want to point out, you didn't have to call it dividing by 3. You could have said, what you were really doing when you were dividing by 3 was you were getting rid of this 3, turning it into a 1, right? So you could say multiply by 1 over 3, by 1/3. That'll kill the 3. 15 times 1/3 will give you that 5. And you could be a little nerdier. Probably none of you did this, because maybe the word wasn't floating around in your classroom, but when you're multiplying by 1/3, you're really multiplying by the inverse of 3, the multiplicative inverse. Right, so solving linear equations like this one was all about multiplying by inverses. And that's what we kind of want to mimic for solving linear congruence equations. If I have something like 2x is congruent to, oh, let me think for a second. 3 mod 5. So this has the same sort of flavor as my blue equation, but now instead of an equal sign, I have my equivalence or congruent sign, and I don't just have 3, I have 3 mod 5. So here's what I'd like to do. I would love to divide by 2, right? Just like I did dividing by 3 in my equation above. Okay, except here's a problem. There's one number you can never divide by. This is worth me writing down. You never, ever, ever divide by 0. Ever. And when we were in just regular algebra land, like in the blue example, that works out just fine. The number 3 isn't 0, so I can divide by it. I can multiply by its inverse. But when we're in mod land, let me scroll up, you might have elements that are like 0 that you can't divide by. You might have 0 divisors. So if we want to divide by 2, whatever exactly that means, what we really want to make sure is we'll make sure 2 isn't a 0 divisor. Equivalently, right, if I'm comparing to how we reworded the blue equation above, quote-unquote dividing to get rid of that coefficient was the same thing as multiplying by 2 inverse. So if I want to quote-unquote divide by 2, it can't be 0. It can't be a 0 divisor. That should be the same thing as saying I want to multiply by its inverse. So I say, okay, is 2 invertible mod 5? Is there a number mod 5 so that 2 times it is equal to 1 mod 5? And here's, you can check. Yes, you can check that 2 times the number 3 is 6, which is 1 mod 5. So the inverse of 2 is 6, at least mod 5. And let's see how that's going to help me solve this linear congruence equation. I have 2x is congruent to 3 mod 5. If I want to get rid of that 2, just like I wanted to get rid of this blue 3 up above, I multiplied by the inverse of 3, multiply both sides by the inverse of 2, its inverse is 3. So 3 times 2, right, really you could write that as a 6x, right, if you wanted, and that should be congruent to 9 mod 5. But here's the thing, 3 times 2, that's a 6. If you write what 6x is, that's a 5x plus 1x. And what is this part? What is 5x mod 5? Well, that's going to be 0, right? Because it's a multiple of 5. So 6x mod 5, 6x is already congruent to just x mod 5. Right? In fact, I knew I was going to be able to do that because 3 times 2 was congruent to 1 mod 5. So rather than writing this as a 6, I could have written this as a 1. And then that's got to be congruent to 3 times 3 mod 5, or 9 mod 5. And I just say, okay, but 9 mod 5, if I want to rewrite it, has to be congruent to 4 mod 5. And so what do I see here? I found my solution to this linear recurrence equation. The values of x that work, x is any number that's congruent to 4 mod 5. In fact, if you go back to my equation, 2x is congruent to 3 mod 5, we can just go back and check. What happens when I plug in 4? Well, 2 times 4 is 8, and 8 certainly is congruent to 3 mod 5. Okay, I'm going to stop this video here. Thanks for listening as long as you have. I'll post another one that works out a few more examples of solving recurrence relations. I just want to point out your homework again has a combination of proving things as well as computing things. One of the things you end up reading and completing a proof for, so in homework 9, there's lots of computing examples, which is nice, but there's also some proving things. And it turns out there's now, I want you to still practice using induction. So there are some induction proofs, and then there's more. But one of the results I have in homework 9 is read these incomplete theorems and fill them all in, and their proofs, and you will end up proving the following big theorem, the following collected theorem. If A is not already 0 mod n, we're starting there, then the following two things are equivalent. A is not a 0 divisor mod n. That turns out to be equivalent to saying A is invertible mod n. So I have like 2 or 3 theorems that are just missing little parts that I want you to fill in, and once you read and fill in all the parts and combine the theorems, you get this result. And this result makes a lot of sense, right? I'll go back to the start of this linear recurrence equation to say why this makes sense. If I want to get x all alone, I want to undo that 2. If you want to think about that as dividing by 2, I need to make sure 2 isn't a 0 divisor. If you want to make sure that's getting rid of the 2 by multiplying by an inverse, I need to make sure 2 is invertible. So if 2 isn't a 0 divisor, it should be invertible, and vice versa. Okay guys, thanks for paying attention. I guess the last bit I will say is the rest of our semester, I've sort of finally, I know it's taken me a while, decided on the remaining topics we're going to explore. So we'll keep up with a little bit more, some more division and modular stuff. Not a whole lot more, but a little bit. And then after that, I want to make sure we talk about something called the pigeonhole principle. This is not a very long or deep thing, But it's good to see this in action. And then finally, I want to finish up the rest of this crazy semester with counting arguments. This is what's called combinatorics, but I'm going to do this in a specific way. We're going to get a lot of counting arguments from Pascal's triangle. I figured this might be a kind of fun way to organize our counting arguments in a way that's interesting to comp sci students. Okay, thanks for your continued patience, and I hope everybody is doing well. I will be in touch soon.